This lesson is going to discuss the different parts of the periodic table. So, important things to know is that there are two different parts of a periodic table. There are periods, which are the horizontal rows that go across, and there are groups, which are the columns that go down. There are 7 different periods, starting with the hydrogen and helium in period 1, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon in period 2, sodium in period 3, 4, 5, 6, and then 7. Now these two down here, they actually fit in after these two, but they're taken out so that the periodic table easily fits into a simple shape. So, because otherwise the table would be much, much longer than it actually is. So there are 7 different periods, so 7 different rows. Again, this is technically part of row 6, and this is part of row 7. And then there are 18 groups, and the groups again are the columns that we have. Okay, so those are the different groups or different parts of the table. Now, there are also 3 different types of elements that fit within the periodic table. The first type of element is they're called nonmetals. So most of the nonmetals are over here on the right-hand side of the periodic table. Nonmetals are things that are most commonly required for living organisms. They're more often than not are liquid or gases at room temperature. So it's rare to see them in a solid form, although carbon is very unique and very special in that it is actually a solid at room temperature. And they're also really poor conductors of electricity. Again, carbon being an exception to that rule. There is, however, one right over here on the left-hand side. Hydrogen is also a non-metal. The majority of the periodic table is actually made up of metals. These are what you typically think of: copper, iron, gold, silver, lead, aluminum. Things that are often dug out of the ground or things that we mine for from the earth. They are more often than not solid at room temperature. However, mercury is a unique example in that it is a liquid at room temperature, which is why it's used as thermometers. And they're typically really good conductors of electricity. So you can see the majority, almost all of the periodic table actually consists of metals. There is one other small section, which are called metalloids. It's this little bit of a zigzaggy section here. These are elements that have properties of both metals and nonmetals. Silicone, for example, is a metalloid, so it's easily to work with like a nonmetal. However, it's a really good conductor like a metal. So they're kind of these like little in-between elements that we have here on the periodic table. Okay, so now let's talk about the groups of the periodic table. Again, the groups are the columns of the periodic table. So again, there are 18 groups. We're not going to give names and information about every single individual group because some of them are very similar and so they can kind of be chunked. But there are a few that have very particular names and very particular properties. The first of those is the alkaline metals. It is this in group 1, so the very first column of the periodic table. Notice I did not highlight hydrogen because hydrogen is not a metal. Hydrogen is a non-metal. So it does, even though it hangs out in this area of the table, it technically is not part of group 1. Okay. So group 1 starts with lithium, sodium, potassium, rubidium, cesium, and francium. They are all alkali metals, meaning they're very soft, shiny. They react violently with water, and if you get a chance, you should look up some of the videos to see what potassium and rubidium do with water. We might do a little demo with some sodium. but it'll be a much smaller version than what you would see on YouTube. And what's most important about these is because they are in group 1, they all have exactly one valence electron. Now, if you have not yet gotten into reading about or learning about valence electrons, don't worry, you will. But just know that every element in group 1 has one valence. Um, Atoms, we've already talked about, atoms are neutral, however, they are not stable. So they have the same number of protons as electrons, however, that doesn't make them happy, which is good for us because if all of the elements were stable, then we would not have any type of chemical bonding and we'd be very limited by what types of materials we could have. But because they are not stable, because they're not stable, they do want to react with each other, and they want to react. This group in particular wants to react by getting rid of that one valence electron, allowing it to have a full outer shell. Okay, group 2, similar name, I know it's terrible, but they are the alkaline metals. So we went from alkali to alkaline, ending in INE this time. These are also metals. Again, remember the majority of our periodic table is metal, but these metals are harder. They're shiny metals. They're really good conductors, and since they are part of group 2, they have exactly 2 valence electrons. Now again, they're unstable because they don't have a full outer shell, and if that doesn't make sense to you, don't worry. Once you watch the videos and look at the notes about that discusses valence electrons and stability, it will make much more sense. But what's important to know is they also want to lose those 2 outer electrons. Next, we're going to do a big chunk from groups 3 to 12. So all in here. And again, remember, this is part of period 6, and this is part of period 7. So they fall in here. All of these groups we call transitional metals. They're hard, they're shiny metals, they're extremely good conductors, but they're not incredibly reactive as compared to the alkali and alkaline metals. They're not very reactive. The reason we're chunking them is because they can have anywhere from 1 to 3 valence electrons. It all depends upon the environment that they are in and what they are around. However, just like the other metals, they do become stable by losing those valence electrons. Now, we are going to, for the most part, avoid a lot of these elements when it comes to dealing with valence because of the fact that there is a range and it's not a set pattern. We're also going to kind of chunk these ones right here. Group 13 is called the boron group because boron is at the top of the column. They have 3 outer electrons. Group 14, the carbon group. Okay, we're getting into our metalloids and starting to turn into our nonmetals. But group 14 has exactly 4 valence electrons in this group. Group 13 wants to lose those 3 electrons in order to become stable. Group 14, it can go either way. Depending upon the situation, it may want to get rid of its 4 valence electrons. Sometimes it wants to gain or share valence electrons, but either way, it needs to either get rid of 4 or to gain 4 more. Group 15 is the nitrogen group. Again, because nitrogen is at the top. Group 15 has exactly 5 valence electrons, and it will become stable by gaining another 3. It wants 3 more electrons to fill its outer shell. Group 16 has 6 valence electrons, and it wants to gain 2 more electrons. Okay, and so they don't have special names. They're just named by the element that is at the top of the column, those 4 groups. Group 17, however, does have a special name. They're called the halogens. Think about halogen lamps or halogen light bulbs. They are very reactive. They are the non-metal version of the alkali metals. So the alkali metals are extremely reactive and the halogens are extremely reactive. The only difference is that the halogens are nonmetals and the alkali metals are obviously metal. So the halogens have 7 valence electrons, which means they only need 1 more electron to fill their shell. And it's because they only need 1 that makes them so extremely reactive. And then finally, group 18, we have the noble gases. The noble gases are non-reactive. They are completely full in their outer shell. They do not need to lose or gain any more electrons. And because they are full, they are stable, and therefore they don't react with other elements. They just kind of hang out there. They are all colorless and odorless gases, but what's interesting about the noble gases is that when you run electricity through them, they actually glow. And it is the noble gases that creates neon lights. So neon, obviously, is right there, but every noble gas glows a different color. And so when you see like an open sign at a restaurant, those tubes are full of these gases, and then when the electricity is plugged in, then those gases actually glow, and that's what creates the neon glow of the lights. Okay, you may have noticed we didn't talk about hydrogen because, again, hydrogen was not part of the alkali metals because it is a non-metal. Hydrogen is like the honey badger of the periodic table. It does not fit into any other category. It acts like a metal because it has 1 valence electron, but it is actually a non-metal, so technically it doesn't fit that group. Now, it has exactly 1 electron because it has exactly 1 proton, and it is not stable. But what's interesting with hydrogen is when it loses its electron, it's no longer an atom. In order to be an atom, you have to have a nucleus with electrons going around the outside. So when hydrogen loses its electron, it no longer exists as an atom. It actually becomes just a pure singular proton. So it's special and therefore has its own special group. Okay, so putting it all together, this is what our table looks like. Again, we have our nonmetals here outlined in pink. We have the metals outlined in dark blue, and our metalloids outlined in green. We have our groups designated as group 1 is the alkali metal. Group 2 is the alkaline metal. All this gray is the transitional metal. Group 13 is the boron group, 14 the carbon group, 15 the nitrogen group, 16 the oxygen group, 17 is the halogens, and 18 is the noble gases, or sometimes called inert gases. Inert just means non-reactive. And then finally, hydrogen over here all by its lonesome. Now, hopefully you've noticed that the table is set up in such a way so that the valence electrons go 1, 2. We ignore this whole middle section because it's a kind of a bit of a mess. But then we skip over that and we go 3, 4, 5, 6, 7, 8. So we are able to figure out how many valence electrons any element of the periodic table, minus this pit of despair here, this middle section, we are able to figure out exactly how many valence electrons these atoms have.